This is circular extensions, IB12. So this is a ramp. We're gonna have a little block and we're gonna fling it with some velocity. And it's gonna end up here. Take a guess, maybe do it in pencil. Draw the free body diagram for that block as it's moving. It's still moving upwards.
Do we have friction?
Let's say no.
And you're just pushing it once, right?
You literally just go. And it goes.
At point 2. The free body at point 2.
What do you mean point 2?
Or wherever the second part is.
Yeah, here. Yeah. Oh, you could do the original too. Tell me the forces involved.
Force of gravity, normal force,
And gravity.
Luke had a good idea actually. Let's do both of these. So you have. This is FG. Is that FG going to change?
Technically, yes.
Oh, because of the gain in altitude
Yes.
of your 20 centimeter ramp.
Oh, it's negligible, but it's gonna be
You see what I have to do. Gravity's gonna be the same for all intents and purposes. That's not changing. Down here you also have what other force? Normal force, good. And that's pushing up with the same as gravity because we're not falling through the table and we're not flying into the air. There might be friction or might not. If there is friction, then you'd have to have an applied force to maintain a constant velocity. What if there's no friction?
No.
Then you don't need one, right? It's just flying along. What's gonna happen to that normal force here?
It's gonna be a separate.
In what direction is it gonna be? Colin's going like this. Yes. It's gonna be, I'll draw it from here. It's gonna be out like that.
Does that mean that the force of gravity is like split into like different components?
So, think about this. This is where kids often get kind of bamboozled. So, if you componentize this like that, can the normal force be in a different direction? No, it has to be normal, right? Normal meaning perpendicular. It has to be perpendicular to the surface. Can it be bigger? Yes, it can be. In fact, this is going to have to be bigger than the perpendicular component. Well, does it have to be? Yeah, it has to be if it's going to keep moving. So it can't be just the same as this perpendicular component. It has to be bigger. So if it's going to go like, you can draw it like that. What's that going to produce? Acceleration. Ben, say that again.
Centripetal acceleration.
Centripetal acceleration. So there's a couple of things going on here, right? So this kind of extra bit here is going to produce, as Ben said, I'm going to do a little arrow here. Say that extra bit is going to produce our centripetal acceleration. Now, If we did a free body diagram of this and we said, well, or if we added our vectors, we would say this is our FG. I'll try to draw it like similar size. And then if we added our centripetal motion here, FC, or we'll say FN, that's FN. What's our net force? What direction? Kind of like this, right? So this would be our F net. Is that exactly to the center of the circle?
Not really.
No, because normal has to be exactly to the center, right? Okay, so what's going to happen to this object?
It's gonna go.
Now you're thinking.
It's gonna go along.
It's so interesting. I love watching student reactions. It's like, yeah, it's going to go like this. And then Dow's going. And then there's this sort of moment where they're like, you know, what does it do? Which is the right reaction. What does it do? Colin, what do you think? Okay, good. So some kind of non-uniform acceleration. Are we gonna be able to maintain our linear speed around the track? I don't think so. It's gonna have to, is it gonna speed up or slow down? It's gonna slow down in what direction? Let me ask you this, is this thing gonna fly off the track? No. Is it gonna break through the track?
No.
Not if it's strong enough. But what can it do?
Go along.
It can increase speed or decrease speed tangential to the circle, right? What's gonna happen here? It's gonna decrease, right? Because if normal force, let me focus in on this bit. If our normal force is just equal to this, that means that you should actually be decelerating in that tangential direction. Does that make sense? So you're actually, because there's no net force towards the center of the circle, you're not going to be able to maintain uniform circular motion. Because uniform circular motion, you have to have your net force right to the middle. And it can't be off. So without friction, there's actually no way to keep your velocity exactly the same. Like, there's no way to keep your speed the same as you go around the loop, right? Unless you add what? Yeah, Colin's going like this. Yeah, you push it. Unless you put a jetpack on here, or some wheels with an engine, or some, you know, something pushing it, right? And then if your applied force, what would your applied force have to be equal to in order to? Yeah, if you go equal to this kind of FGX component, then you're fine. You can keep your velocity all the way around.
So wouldn't you require to change the speed, like the force of the jetpack while going up and down?
Well, you tell me. Would you?
Yeah, I think the more elevated you are,
The less it X.
because the angle changes of the
Right, so if you're here at this, I won't draw it just yet, but if you're, well, okay, let's draw it. Let's do another circle. Try to find something circular. I'm gonna use tape this time.
That works.
Can anybody do a good freehand circle?
Well,
Yeah, you can?
Put your thumb down and turn the paper around.
Whoa! Colin, Joe, Colin Joe just like blew my mind. Okay, so you put your thumb on the paper, you put your pen down, and you turn the paper around your thumb. If this works, oh,
That's pretty good.
it works. Oh my
oh
god.
boy, oh boy.
That's actually good.
Wow, it's massive. But it works pretty good. Well done, Colin. Well done.
By the way, you have a low battery.
Just hold like
Oh. Does anybody have a charger cable?
not that long.
Sorry, Eric. I tried.
Oh.
It's gonna die, and then the video won't save. I'm gonna stop it.
Little.
You have to close the wording.
Oh, thank you.